See, in case of SN2 reactions, the presence of heteroatom on alpha carbon in halides increases reactivity of the substrate. Okay. It is because the lone pair of electrons present on the heteroatom stabilize the transition state by resonance. Okay. So having a heteroatom on alpha carbon stabilizes the transition state by, you can say, the plus M effect. I mean, because of the lone pair of electrons present on the heteroatom, the transition state gets stabilized. Okay. Let me give you an example. Okay. Look at this. So this is the alpha carbon, has got a heteroatom attached. Now, as and when the bromide goes off, the pair of electron on oxygen comes into picture and it stabilizes the transition state. Okay. Let us treat it with potassium thiol, upon which we get this. Okay. Now this is how Br minus is replaced, substituted by SH minus. This is an important point. And one more very, very important point. The presence of carbonyl group at alpha carbon is most suitable for SN2. Most suitable. Look at this. Having a carbonyl group at alpha carbon. In general, electron withdrawing group increase the rate of SN2. Okay. This increase in rate of SN2 is really surprising. If you observe the percentages of the rate of reactivity let me first give you an example, then we'll give you percentages or the rates of reaction, the comparison of rates of reaction. See this. Now when treated with acetate, see here you got a carbonyl group at alpha carbon, I mean attached to alpha carbon. This is what we get. The chloride ion is of course replaced. Okay. Yes. Now let us check the relative rates of SN2 reaction. Of alkyl chloride with iodide ion. This will give you the clear picture. Alkyl halide, relative rate of reaction, and the reason are the common. Now let us take the simple methyl chloride. Maximum. Because of course the methyl group is least hindered. Because it is least hindered, easily attacked by the nucleophile. If you go for this, look at the relative rate. It is actually because of steric hindrance. 3 degree, we don't actually consider. These are all experimental results. So this is allyl chloride. The relative rate is this. It is because of pi conjugation. Now, the carbon to which halogen is attached has this pi bond in conjugation. So pi conjugation is very much possible in this. Coming to this. Now this is benzyl. This is allyl chloride. And this of course is benzyl chloride. Now, in case of benzyl chloride, you know the relative rate of reactivity is again 200. See, it has more pi conjugation than the allyl thing or than the isolated double bond. Now look at this. MEO then Cl. Yes, just now I told you this very important point that when you have a heteroatom at the alpha carbon, that will give more rate of reaction. Okay, conjugation with the lone pair on oxygen. Okay, and finally, look at this. This is super. You got a carbonyl group at alpha position to the carbon that has halogen. Okay. I can tell you that it is because of effective conjugation, more effective conjugation than others. Okay. Let me tell you what that effective conjugation is now. See, the basic mechanism of how the reaction happens can be given this way. Let me first give you the mechanism. Now, when the nucleophile attacks this carbon, this will go off. Now, look at what happens. This is oxygen. Oxygen. this is the other bond that we have. See, in this case, it is the pi star, I mean the anti-bonding molecular orbital of the CO bond. Now see, the nucleophile is attacking okay. Now this is the sigma star of the carbon bromine bond. So this kind of a conjugation can be seen between, see, this is the pi star of the C double bond O, and this is the sigma star of the carbon bromine bond. Okay. Now these are in better conjugation. That can of course be shown this way. This is very interesting. Now bromine is going out. One lobe has actually got, I mean, it has overlapped with bromine and the other one with the nucleophile. This actually explains the backside attack of nucleophile. One lobe overlaps with the nucleofuse, I mean the leaving group, whereas the other one overlaps with the nucleophile. This is very interesting. You cannot have the same kind of attack of the nucleophile from the front side, because now one lobe has to overlap with both. That is not possible. Okay. Now finally you get this. You still got a bond here. Then this. Now you got the nucleophile. So the pi star of C double bond O bond is the one that actually stabilizes. Okay. So this is the conjugation that actually helps increase the relative rate of SN2 reactivity. Okay. Now let me also give you two more important points with regard to SN2. Of course, SN1 also. Coming to vinylic and phenylic halides. You know, these are unreactive towards both SN1 and SN2. For different reasons, these are unreactive towards both. we know that the vinyl group is this. So this is the vinyl halide, and coming to phenyl halide, it is this. Okay. So as far as SN1 is concerned, we know that SN1 goes via a more stable carbocation. Okay. But we know that the vinyl carbocation, I mean, once it loses the halide ion, we get a vinyl carbocation. Which is unstable, least stable. And even when you go for the aryl or phenyl halide also, when the halogen is lost, you get a phenyl carbocation. Even this also is unstable. Why? It is because, you know, the positive charge cannot be delocalized. If it were to be of this type, it would have been okay. This would have actually gone to the rescue of the positive charge. That would have actually given a possibility for conjugation, delocalization. Even here also, you got both positive charge and the pi bond at the same carbon. Okay. So now, let me tell you that in these two cases, the positive charge cannot delocalize. So they are with zero resonance, therefore they are not the stable ones. Least stable, or you can say unstable. This is the reason why they do not undergo SN1. Now, let us see why not SN2. As far as SN2 is concerned, look at the bonds. Now in these two, the carbon halogen bonds are sp2 carbon halogen bonds. Even here also, this is of sp2 type. And even here also you got sp2 carbon halogen bond. Now, because the bond here is stronger when compared to sp3 carbon halogen bonds in alkyl halides, what we see generally, these do not undergo SN2 also. The carbon halogen bond in vinyl and phenyl halides is stronger than the carbon halogen bond in alkyl halides. So this is very interesting. Here it is sp2 carbon halogen, whereas here it is sp3 carbon halogen. Okay. The double bonded carbon halogen bond is stronger, so are less reactive. In fact, unreactive towards SN2. Okay. Now let us go for SNI, nucleophilic substitution internal. Let me give you an example. See, alcohol with thionyl chloride. Let us remove a HCl. Then of course we get ROS double bond O Cl. This is called alkyl chlorosulfide. Now, with the thionyl chloride, in the absence of pyridine, okay, so this is thionyl chloride. Now, in the absence of pyridine, we get alkyl halide, SO2, and HCl. Okay. Now, see the mechanism, which is very interesting. Let us take the three-dimensional structuring of the alkyl chlorosulfide. Now, in the first step, which is the slow step or the rate determining step, this goes off. And we get a carbocation. C plus. But you know, immediately the thing that has gone out attacks this positive ion from the same side. This is important. Now, there is some controversy with regard to this mechanism, whether it occurs in two steps or in just one step. I mean, this and this, both, whether they occur in just one step or in these two kind of steps, there is a controversy. But still, the very important point here is the same side attack, which gives us 100% retention product. Now, okay. And of course, the sulfur dioxide is eliminated. So here we get 100% retention product. In the absence of pyridine, it is SNI. In the presence of pyridine, it is SN2. We know that. See, in this case, rate can be given as directly proportional to the concentration of alcohol to the power 1, even thionyl chloride to the power 1. Therefore, it follows second order kinetics.